Hello everyone and welcome back to Not Only Math. Thank you so much for joining me here today as we continue our study of ratios, rates, unit rates, and proportions. Today we're going to build on an idea we talked about in our last video, which was rates of change, and we're going to explore more closely this idea of a constant rate of change. So let's go ahead and just dive right in today. You'll remember, hopefully, in our previous video on rates of change, I gave this example about meters and seconds. And we talked about the fact that when we're discussing a rate of change, we're not looking just at any particular rate between meters and seconds, not any particular rate, but rather we're looking at how the two different items are changing at the same time. So I'm not so much concerned about the fact that this is 20 meters and 3 seconds as I am how quickly we went from 0, 0 up to 23. And we said that we can actually calculate that as change in time over, or change in meters over change in time. And then we talked about how we could abbreviate that as the change in meters using delta, or the Greek letter D, delta meters and delta time. And we said, we're going to look at how we go from 0 to 20 meters in 3 seconds, and how these numbers right here can be calculated by subtracting whatever our ending value was from our initial or starting value, 20 minus 0 and 3 minus 0. And we said that gives us a rate of 20 meters in 3 seconds. And then in the previous video, we went through and we said we can do that for any pair of meter and second rates. So I can go through in here and say, okay, well, from 20 to 40 and from 3 to 6 is a change of 20 and 3. Or we get that by subtracting end minus start, end minus start. And we said this also came out as 20 meters in 3 seconds. And then we did the exact same thing for the other ratios. And in our previous video, we said that in every one of these changes, we're changing at the same rate, 20 meters in 3 seconds, or as a unit rate, 7 1/3 meters per second. And then we said in the previous video that just because this has a constant rate of change does not mean that every single set of rates that we are given will have a constant rate of change. So we always have to be attentive to that. Now, we did say this rate of change is constant, and we want to look at specifically rates that have constant rates of change today. So you can see here what I have done is I've copied the table from the previous slide and also from the previous slide show onto this slide, and I've also added a distance time graph. So I've got a coordinate plane up here that shows seconds along the x-axis and meters along the y-axis. Now on the previous slide we already said that we can calculate the change in meters over the change in time as 20 meters in 3 seconds and 7 1/3 meters per second. Remember, we had to do that for each change, and we found they were all the same or they were constant. So what I'm going to do is I'm going to plot these rates as coordinates on my distance time graph. So you can see my first coordinate is going to be 0 meters, 0 seconds. So I'm going to go down here to the point 0, 0, and I'm going to put a dot. Then I'm going to go to the right 3 spaces over 3 seconds, and I'm going to go up 20 meters, so over 3, up 20, and I'm also going to put a dot here. Notice that these 2 points represent these 2 ratios. I'm then going to more quickly do 6 seconds and 40 meters, 9 seconds and 60 meters, 12 seconds and 80 meters, and I'm going to look at those dots on my graph. Hopefully you can see that there is something important or significant that pops out at you. If not, pause the video, take a second and think about that. I'm going to assume you've already figured that out on your own. I'm just going to go ahead and tell you that it's interesting that these all form a straight line. Now all lines are straight, but I do like to say straight line because we have looked at some graphs that were made of multiple line segments that had a graph that kept changing the speed at which it was growing. What's significant to us here is because we have this constant rate of growth, we're always growing at the same speed, and that's going to cause us to have a straight line. In other words, because the rate of change affects how slanted the line is, the slope of the line is never going to change. The steepness or slantedness is always going to be increasing 20 meters in 3 seconds. I'm always going to go up 20 meters over 3 seconds, up 20 meters over 3 seconds, up 20 meters over 3 seconds, up 20 meters over 3 seconds. The steepness is always going to be the same, or the slope is always going to be the same, because we're always going up the same amount when we go over 3 seconds. Now, a pattern with a constant rate of change will always form a straight line when graphed. The pattern is said to be a linear pattern because the graph looks like a straight line. Now, I spent a lot of time on this slide because there are several very, very important concepts we have to pick up here that are important for us when we begin talking about linear algebra, or the algebra of linear relationships. And that is this: the rate of change and the slantedness and the slope are all three ways of describing the same thing. The rate of change, the slantedness, and the slope of this line is always the ratio between how many meters I go up compared to the amount of time I go up. That's the first idea. The second idea is that if that rate of change is constant, you will always have a line or a linear pattern. Let's do another one of these. In this graph, or in this table, I'm looking at the rate, costs, and pizzas, a rate that compares costs and pizzas. And there are several rates you can create. You could do pizzas over cost, or you could put cost in the numerator and pizzas in the denominator. You'll remember when we first started talking about rates, we said that it is customary to always put time in the denominator and to always put money in the numerator. So when I look at my rate of change here, I'm going to look at the change in cost compared to the change in pizzas. And because my cost is on top, I'm going to put cost on the y-axis. The numerator always goes on the y-axis. And I'm going to put pizzas on my x-axis. So I'm looking at the change in cost compared to the change in pizzas. Or in terms of the graph, I'm going to look at how my graph rises compared to how it runs or goes side to side. Now, because we've not worked this out already, it is important for us to go through and make sure we know what those rates of change are. There are two different ways we could do that. We could start off just by subtracting the end minus starts and saying I ended at $18, I started at $10, I ended at 1 pizza, I started at 1 pizza, and I get a unit rate of $8 per pizza. And then I could go through and do the same thing for the second pair. I end at 26, I started at 18, I end at 2, I started at 1. That's a change of $8 per pizza. And I can do that change between any of these pairs of points, or between all these pairs of points. And you will notice that we do have a constant rate of change, $8 per pizza. Once I know that the rate of change is constant, I know that when I graph this, my graph should be a straight line. So I'm going to plot all 5 of these points. I'm going to go ahead and erase those ink marks. There we go. So my cost is $10 when I buy 0 pizzas. 10 is right here. We're counting by 4s. 4, 8, 12, 16. So 10 is going to be here. It's $10 for 0 pizzas. I go up to $18 when I buy 1 pizza, $26 for 2 pizzas, $34 for 3 pizzas, and $42 for 4 pizzas. Notice those all fell in a straight line. This is a linear pattern because it does have a constant rate of change. Now, this one's a little different from the previous one because you'll notice that we are not starting down here at 0, 0. Linear patterns don't have to start at 0, 0. This one happens to start at 10. Students sometimes ask me, well, how would they charge me $10 for 0 pizzas? Well, there's a lot of reasons you might think of it this way. You might say, well, there's a $10 delivery fee plus a cost of $8 per pizza. This initial delivery fee would be why we're starting up here instead of down here at 0, 0. The delivery fee only happens one time, and that's regardless of how many pizzas you order. So we call this one-time charge our 0 point. And then it's $8 per pizza after that. Notice, by the way, we didn't start at 0, 0, but we did rise $8 when we bought a pizza, rise $8 when we bought a pizza, rise $8 when we bought a pizza, and rise $8 when we bought a pizza. We have that constant rate of change that causes this to be a straight line. Not too bad, right? One thing I do want to make sure I point out as well, even though this has a linear pattern or a constant rate of change, these ratios or rates are not proportional. This is not a proportion because if I use my means extremes property, you can see that these multiply together to give me 10, these multiply together to give me 18. Now, in a separate lesson, we'll talk about what it means to be proportional in a graphical sense, but for now, just know that proportions will always be linear, but just because something's linear does not mean it is also a proportion. Here's what I would recommend that you do. I would recommend that you go ahead and pause the video. You try this one on your own. See if you can find these constant rates of change and then determine whether this will be linear or not. And then we'll go ahead and graph these to see if it does indeed make a straight line. Notice I did put my square inches on the y-axis. So square inches is going to be on top, and square feet is going to be on bottom. So just make sure you're careful when you set that up. It does make a difference in terms of how we do the graph. I'm going to assume that if you are actually going to take the time to find your rates of change, that you've already done that. So I'm going to do this quickly. I do my ending point minus my starting points. 144 square inches per square foot, 144 square inches per square foot. Notice here I got 288 square inches per 2 square feet. That does simplify to 144.8. And my last pair gives me 576 square inches in 4 square feet, which also simplifies to 144 square inches per square foot. When I graph those, my first point is 1, 144, 2, 288, 3, 432, 4, 720, and 9, 12, 96. Notice that those do indeed form a straight line. This is a linear pattern because it does have that constant rate of change. Notice I went up 144 over 1, up 144 over 1. Here I went up 288 over 2. That's an interesting point because, we'll switch inks here. That's an interesting point to me because basically what you've done is you've done two steps at once. This would have been up 288 over 2, and it is the same. Here you went up 576 over 4. That would have been the same as up 144 over 1, up 144 over 1, up 144 over 1, up. This would be the same as repeating that ratio 4 different times. So just know that when you're looking for your constant rates of change, you need to be looking at the simplest form of those fractions, or the unit rate, because you could get fractions where, or ratios or rates, where you are climbing multiple increments at a time. Not too bad, right? And there you can see the for the whole thing, it's 1152 over 8, which is also, oops, 144 square inches per square foot. Here's another one. I'd suggest you pause the video and try this one on your own. This is the last full one I believe that we're going to do. We'll summarize things after we're done with this one. It says find the constant rate of change for the hours traveled and miles traveled and interpret its meaning. Hopefully you can look at this, and now that you know that we are examining the ratio between miles and hours, now that we know that the y-axis is our numerator and the x-axis is our denominator, we can calculate the slope or constant rate of change using how much we rise compared to how much we run. In other words, how much am I going up when I go over? or the change in miles compared to the change in hours. Once we see that, all we've got to do is look at our ends and our starts. If I'm going from this dot to this dot, I ended at 75, I started at 50, that's a rise of 25. If I'm going from this spot to this spot, and I'm looking at my hours, I ended at 3 hours, I started at 2 hours. So when I subtract those, I've grown 25 miles in 1 hour. Now, since that is my constant rate of change, you can see that I go up 25 every hour, or you can see that I went up 50 miles in 2 hours, or if I wanted to erase all of this and go back, I could even do a rise of 75 miles in 3 hours. All of those are rates that simplify back to 25 miles per hour. Here's one last one. Use the graph to determine the constant rate of change and interpret its meaning. I'm going to suggest that you pause the video and try this on your own this time. Notice that there are not dots given to you, but you should be able to look at this very quickly and see that there are lots of nice points of intersection that you can use. I'm going to assume that you've already done that if you wanted to, and I'm going to point out to you that any of these points that I'm circling right here are going to be points that you could have used to find this constant rate of change. It really doesn't matter which ones you pick, because regardless of what you pick, you should get the same answer because it has a constant rate of change. I happen to look at this and say, okay, my rise and my run are the change in cost compared to the change in miles. Remember, the numerator, or y value, is going to go on top. The denominator, or x value, is going to go on bottom. So this is charge in miles. And there again, I wrote it using my delta symbol. And we're going to do our end minus starts. These are the 2 points I picked. Notice that the top is my cost. I ended at $12. I started at $8. That's a rise of 4. I ended at 10 miles. I started at 5 miles. That is a change of 5. So you get $4 in 5 miles. Or as a unit rate, you can see that I have a typo here that says 25 cents per mile. That is actually going to be 80 cents per mile. 80 cents per mile. That makes sense? If you get your thoughts organized at the beginning, this part of the problem and this part of the problem end up being much, much easier. So just make sure you're taking your time and realizing what rate of change you are looking for. Now, a couple last things I want to point out. There are 4 different ways that your graph could look. We'll get into these in greater detail in our linear equations unit, but for now, I do want to make sure I point out to you that if you have a positive rate of change, that means that you are going up as you go to the right. You're growing and growing. If you have a negative rate of change, you're going to slant down. That means something is decreasing as time passes. It is also possible that neither thing, or that your item is not growing at all as time passes. And it's also possible that time isn't passing at all. Those are the weird ones, and so we really end up with no rate of change at all. There again, we'll get into that in much, much greater detail during our linear equations unit, but I just want to make sure I pointed that out to you. For our purposes, you're specifically going to want to keep an eye on these first 3. Things that have a positive rate of change, a negative rate of change, or that grow at a rate of 0 as time passes. Last thing, let me give you 2 big ideas, or the same big idea stated 2 different ways to help you tie it all together. If your rate has a constant rate of change, then it must be linear. It will be linear. It will give you a graph that's a straight line. Conversely, if the graph is a straight line, if you're looking at a graph and you can already see that it has a straight line, then you know for sure it must be linear and it must have a constant rate of change. Both of these things happen together. Depending on which piece of information you're given, you can make a decision about the other. So if I give you the ratios, you can figure out what the graph is going to look like, knowing whether it will be linear or not. If I give you a linear graph, you know that your rate must have a constant rate of change. Hope that wasn't too overwhelming for you. I do appreciate you taking the time to watch this and learn along with us. Thank you for joining us. As always, I do wish you all the very, very best of luck. Make sure that you tune back in for our next set of lessons. Make sure you smash that like button, turn on your notifications, ring that bell, all that good internet YouTube stuff. So you guys take care of yourselves. I look forward to talking with you again, all right? Bye-bye.